Hello students. So on this last video for chapter 19, we will go through non-standard conditions and how that can relate, and then start looking at some real-world examples such as like non-spontaneous reactions and how redox applies to our everyday lives. We'll go ahead and get started now. So, while it's convenient to calculate E cell standard, E cell not, reactions rarely occur at 1 molar conditions. And even if they do occur at 1 molar conditions, they rarely stay at 1 molar conditions for very long. So, just like we can calculate G non-standard from G naught, we can calculate E non-standard from E naught. That by plugging in the negative NFE every time where we see a G, we get the following equation. But when we divide by our NF, negative NF, to leave just the E's behind, we get that what we call the Nernst equation, which basically says E non-standard equals the standard cell potential minus RT over NF ln Q. So if we know the concentrations of both solutions, we can figure out how the actual cell potential may vary based on the number of electrons and a bunch of constants and the temperature. So, well, you'll notice, of course, as temperature increases, you're going to have batteries aren't going to work as well. But largely speaking, remember when at standard conditions, Q is 1 and ln Q must equal 0. So at standard conditions, the E non-standard is essentially the E standard. And when Q equals K, that's when the rare conditions where the E non-standard approaches 0, because basically as the battery discharges, the cell potential will trickle off and die and go to 0. So we can figure out that. So all that's fine. But with that in mind, we can calculate the new voltage, and the voltage can be strengthened or weakened by giving certain non-standard conditions. We can tweak the voltage slightly based on certain changes to the half reactions. Which brings us to a really kind of annoying but somewhat interesting idea called concentration cells. Like, E non-standard's dependence on concentration leads to unusual situations that you can have two half cells that are essentially the same reaction. You can have like copper going to copper 2 plus and copper 2 plus going to copper. And normally the cell potential between those two is 0 because E standard, A minus A is always going to cancel out and leave you 0. But if you have a difference in concentration between the two of them, you're basically trying to reach equilibrium. You're trying to reach the half reaction where the concentrations are essentially the same. It's kind of like an osmosis, but it's separated by the salt bridge and the wire. That essentially one guy will decompose a bit, and the other guy will one guy will oxidize a bit, and the other guy will reduce a bit until they get essentially the same concentrations on both sides. So by varying the concentrations from one cell to another, you can create a small but significant voltage. Now, this is the basic idea of how electric eels work. This is kind of, in some ways, the way that the mitochondria work. We essentially, you're shuttling out protons or electrons from one side to the other. And as you shuttle out these molecules, you're creating a difference in concentration. And they want to recombine back together. They want to get back at equilibrium. You're putting a non-equilibrium system into effect, and then equilibrium wants to reestablish, and that creates a non-zero voltage. So essentially, the electric eels have ways to essentially shuttle hydrogens across membranes so that when they need to, you get a small concentration difference that can create essentially a redox reaction that creates a shock that's capable of stunning predators and killing prey. So just looking at an example where, just for simplicity's sake, we use 1 atmosphere of hydrogen in both cases, but we use a pH 3 and a pH 7 cells. That the pH 7, so you got to remember our Q for each half reaction is going to be, when hydrogen is on top, it's going to be hydrogen over H plus squared, and when you got the oxidation, it's going to be H plus squared over hydrogen. So in this case, we have a 10 to the negative 7th on top squared and 10 to the negative 3rd on bottom squared. Now you do that, and you do the natural log of that, and multiply by all those constants, and what do you get? You get a voltage of 0.236. Now, this is not necessarily a huge voltage, but it is not a tiny voltage. It's not super spontaneous, but it is indeed spontaneous. Now, in most situations, the Nernst equation won't vary by that much, but from the E cell standard, but this is a special case. Essentially, one concentration cell is 10,000 times greater in concentration. So that is a kind of a significant difference, and so that makes a big voltage difference here. But just looking at this, okay, sodium hydroxide. So water can, if you put sodium in water, you get hydrogen gas and 2 sodiums and 2 hydroxides. This is an explosive reaction. And I have the Na plus electron goes to Na solid, 2.71, and I have the water, 2 waters plus 2 electrons goes to H2 and 2 OH minus, and that's negative 8.3. Now, if I dissolve enough sodium that it would produce 0.25 molar NaOH, and we have 0.00075 molar hydrogen gas. What is the E non-standard at 25 degrees? First, we need to figure out what is the E cell standard. What is the E cell standard of this? The E cell standard is going to be, so this occurs as written, and this has been reversed. So the E naught is going to be negative 0.83 minus a negative 2.71. A negative, of course, is a positive. So I'm going to, negative 0.83, and we're going to add the 2.71, and that's not going to be a plus. And so 1.88 volts. Okay, 1.88 volts. That's if this was 1, 1, and 1. These don't matter because pure liquid, pure solid. Now our Q is going to be Na plus squared OH minus squared and H2. So our Q is, well, I'm going to plug in our numbers. We have 0.25, 0.25, and 0.0075. So 0.25 squared times 0.25 squared times 0.00075. Let's turn that into scientifics just so I can read that. And so that gives a Q of, this is a Q that's rather small, 9.2, let's say 9.7 times 10 to the negative 6. So with that in mind, our E non-standard is going to be equal to the E standard, 1.88, minus R minus T, 298, divided by N, 2 electrons, 1 electron, the greatest common factor is 2, F, 96485, times ln of 2.9297 times 10 to the negative 6th. So let's start with our log, or natural log of that. Log of my answer times negative 8.314 times 298 divided by 2 divided by 96485. So all said and done, the small effect, we are tweaking this value by a factor of 0.16. So when I add this to my E cell standard, my voltage goes up to 204. It's not a huge leap, but it is enough that if you ignored this and you tried to do the math, you would get it wrong. If you just did the E cell standard, it would be wrong. But all said and done, it is not a huge change. Nernst does not improve things by a lot, but it does change the voltage. So once again, much like when we talked about buffers, the starting buffer controlled where the pH of it would be once you manipulated it. Well, the starting concentration cell, or the starting cell potential, is going to be largely to control what voltage we can get out of this. But the Nernst allows us to tweak this a little bit higher, a little bit lower, as we see fit. Now, another big issue that we need to discuss is electrolysis. Electrolysis is a process by which we make a non-spontaneous reaction spontaneous. Not all redox reactions are necessarily spontaneous, because for every reaction we can write forward, the reverse reaction can happen, but it is non-spontaneous. E cells being negative do not mean they cannot occur, it just means they will not occur on their own. You could put basically a battery will naturally want to discharge over time, especially if the cells are perfectly connected. However, batteries can be rechargeable by putting in energy. Otherwise, our lead acid batteries that run our cars would not work. We would need to be able to recharge them, and the alternator's job is to do that. But so not all cell reactions are spontaneous, but some are worth the effort. So electrolytic cells take an input voltage and they force a non-spontaneous reaction to occur, such as splitting salt into its component elements. So if we want to form pure sodium and chlorine gas, you could take a salt reaction and run a current through it, and there you have sodium chloride, or sodium and chlorine gas. The most common use we will use is to electroplate objects, chrome plating in cars. Now, this process is not instantaneous, it is not automatic, but if you know about voltage and current, you can calculate how long it takes to deposit certain amounts of metal. What is probably most interesting is this electrolytic process. It both created and destroyed the aluminum industry. Aluminum used to be a very rare metal, one that you could not get easily, and so it was very costly to get aluminum. But Alcoa found that through electrolysis we could easily turn the aluminum oxide that we can dig out of the ground into pure aluminum very cheaply and efficiently. And so overnight he made, well, not really overnight, but essentially made millions, but also drastically dropped the price of this rare metal because it was now incredibly easy to make this, and so you can essentially flood the market. But so this process, to do this, as I said, you need current to do this. Current is essentially the rate or speed of which electron transfer occurs. It is measured in amperes, but the amperes essentially has another definition, which is a coulomb per second. So just like a velocity might be a meter per second, a coulomb per second is how many charges, how many electrons are essentially transferred in a period of time. So if we use the coulombs along with a time and the molar mass and our N and F, we can essentially calculate how long it would take to transfer so many moles. So if we take a current times a time, that's going to say how many coulombs could be plated at this time. By using N and F, we can figure out essentially how many moles of product can be plated using that many electrons. And then using the molar mass, we can convert, of course, moles into grams of product. From there, you could do a lot of complicated math based on surface area to figure out thickness of sheet, but we won't bother to do that. But the equation is essentially mass equals current times time times molar mass over NF. And if you look at your units very carefully, coulombs per second times second cancels the seconds. Coulombs with Faraday's constant gets us to moles of electron. The N gets us to moles of product, and then the moles of product gets us to grams of product with the molar mass. And of course, you could also rearrange this to find time instead if you have a mass, or current if you needed current. It is a rather simple equation as long as you know how to rearrange it and you know the terminology. But so how long would it take to electroplate 20 grams of chromium 3 plus? So 20 grams of chromium 3 plus if I use a current of 5 amps. And then how much zinc 2 plus could be electroplated in 1 hour at 10 amps? Please note that current is coulombs per second. So any time period, you have to convert those into seconds for that to work. But one thing I need to look up real quick is the molar mass of chromium, which will say it's about 52. It's like 51.996, so it's about 52. And zinc is about 65.4. So, I'm given, we got a mass, we got a molar mass, we got a current. Faraday's is always 96485. The only thing we need is N. We're usually trying to get to a neutral state. So N is going to be 3. N is going to be 2. So if my equation is M equals I T M over NF, rearranging this, it should read mass times NF over molar mass times 1 over I is going to be our time. So 20 grams times 1 over 52 times 3 times Faraday's, 6.485 times 1 over 5 amps. So I'm just plugging that in. I've rearranged my equation. I'm plugging that in. So 20 divided by 52 times 3 times Faraday's, 96485, divided by 5 amps. It's a big number. But remember, this is in seconds. So let's convert this into something a little bit more reasonable. So 60 seconds in a minute and 60 minutes in an hour. This would take something like, in time, 6.18 hours. 6.18 hours to electroplate 20 grams at 5 amps. If I want to know how much mass can be delivered after 1 hour in 10 amps, we got our time. 60 times 60 times 1 is our time. So we have a current 10 amps times 3600 time in seconds times a molar mass of 65.4, but then we have to divide that by 2 and Faraday's. 2 Faraday's. So how much could be delivered? 10 times 3600 times 65.4 divided by 2 divided by 96485. It would deliver something like 12.2 grams. Not a whole lot, but I mean, 12.2 grams is nothing to really scoff about. So you run this for a period of time, and you can electroplate, and you can calculate how much you deliver based on what you're trying to do. And so, with that in mind, that is a real quick example of electroplating. Now this last little bit will be all about some real-world examples, such as batteries. How do they work? Now, I have in here some charts. You can see over here energy densities, both by mass and by volume. And you can see diesel is by far the highest energy density of our fuels, followed closely by gasoline. Then moving downwards, we have E85, so it's mostly ethanol fuel, and then followed closely by ethanol, pure ethanol. Then M85, which would be mostly methanol fuel, then methanol. Then we have over here our common burnable gases like liquid hydrogen. So you've compressed it enough to liquefy it. Pressurized methane gas, pressurized hydrogen gas. So just storing hydrogen as a gas under high pressure. Very low energy density, but then again, it's a lot cleaner. And so some of these guys are kind of more easily renewable, even though they have lower energy densities, which is why we kind of use them. Now, if we look way down here, here's where our batteries are. If we blow that up, we can look at various batteries. We have zinc air batteries. We have lithium-ion systems of various types. We have nickel metal hydride, nickel cadmium, and way down here on the very bottom is lead acid. Lead acid. So batteries are very low energy density and not super great. But however, batteries serve a major purpose in that we can easily store them for a long period of time. They can store energy that can be charged up from renewable sources, and they can release it safely, usually, over a period of time. We can usually go through multiple periods of reuse depending on what they are. I mean, some things are not necessarily rechargeable, but a lot of them are. And a lot of these have low waste byproduct. We can recycle some of these guys and then bring them back and remake them, reform them. You can take the lead acid batteries and you can get the lead out of them and maybe clean them up and reuse some of the products in those. While if you burn methanol and ethanol, it's just going to go into CO2 and water. Maybe you can capture the water, but the CO2 goes in the atmosphere, and it's a little harder to get that back out. So there are certain advantages to these batteries as opposed to our friends, the fossil fuels. Now, I've done a lot of work with lead acid batteries, so I know a little bit more about them than I know about the other types of batteries. But lead acid batteries are probably one of the oldest battery types that we still use today. The basic reaction is we have two lead products, and we have a conproportionation, opposite of a disproportionation reaction, where they come together rather than separating apart. That lead 4 oxide and lead solid on two half reactions in the presence of acid goes to lead 2+. So lead 4 and lead 0 both go to lead 2+. Now, in order to do this, we use a salt bridge, which is our sulfuric acid. So the sulfuric acid serves as both the electrolyte and the salt bridge, that the protons can flow to one side to make it positive, the sulfates can flow to the other side to make it negative as we do this reaction. Now, there are certain things that help and hurt. That, for example, lead sulfate is not super duper soluble, and so we will form crystals of lead sulfate as the discharge occurs. Typically we have a lead grid, and we've pasted the active material onto this lead grid, and so as it discharges, it forms lead sulfate crystals onto this grid, and it gets held on, like kind of like a webbing. It gets held onto there. The crystals kind of form onto this web. Now, this helps with the recharge, because when when you recharge the lead acid battery, you're converting the lead sulfate back into the either lead zero or the lead oxide. And this is very useful when the crystals are small. However, one thing they warn you is don't leave a battery dead for a long period of time. Don't let them stay discharged. If you let your battery die and you don't fix it too long, you're essentially allowing large lead sulfate crystals to form. Basically, the crystals can turn from small crystals into big crystals, and the bigger they are, the harder it is to recharge them and to convert them back into their normal states. And so that's part of why when you let your battery die, it can be bad for the battery's health. Now, this battery contains an anode and a cathode half cells. Now, they don't contain them in separate solutions and separate containers. They keep them in the same electrolytic solution, which in a way this could be bad, because if the two grids touch, they will create a short circuit. But so what we do is we put a porous membrane called a separator. It's basically a giant filter paper that keeps the lead and the paste from both of the active material on their own sides. But it allows the sulfuric acid to kind of seep through. And so as we have this, they can essentially maintain, we can just slap a bunch of these guys back to back to back, and we get more and more and more voltage as we put more and more cells in the same in series. Now, as I said, this is the lowest energy density of all the batteries. However, it is the cheapest. We have a lot of lead out there in the environment, and it only essentially uses lead. And so that's why we still use it. I mean, unless you somehow have some overcharge where it produces hydrogen and oxygen and then you can have an explosion, it's one of the more safer technologies, one of the more rechargeable technologies, and it's one of the cheaper technologies, as opposed to a big-ass lead battery works a lot more efficiently than you have the tiny like lithium-ion batteries for your computer, and those cost a lot more. So they're relatively cheap for what they can do. Now, other batteries, they have different processes. So, for example, alkaline batteries are AAA or AA or D cells. A lot of those work by a different half reaction where they use manganese and zinc. They're called alkaline batteries because they use a highly basic solution, so they're under basic conditions instead of acidic. Now, a lot of these are not rechargeable because the nature of the products, that lead sulfate crystals help with the rechargeability of the batteries, but these guys, if it forms the product and the product floats to the bottom of the battery, you can't actually put it back on. If it floats away from the grid, you can't easily put it back where it needs to go. And so either the battery starts to explode or it sinks to the bottom, and basically you cannot get the energy back. You have some things like nickel cadmium batteries or nickel metal hydride batteries that they have a lot higher energy densities and rechargeabilities, but they're less useful just because cadmium is uber toxic, and the nickel metal hydrides need lanthanide metals, which lanthanides are the rare earth, very rare metals, and so they highly costly. So it's like harder to get, so the cost goes way up. Now, lithium ion, I'm not sure if this is still true, but when I originally wrote this, lithium ion batteries, they work in a different mechanism that's a little bit harder to understand. that the electrons in the other batteries are transferred. In these batteries, instead, we have a lithium ions that are kind of ping-pong balling from one side of the electrodes to the other. We have a copper oxide electrode and a graphite electrode, basically a carbon-based electrode. But as I said, the half reactions of these guys are not as well defined, not as well understood. We know it works, but it's not easier to just put it down in a chemical formula. Now, the other big redox reaction that happens everywhere is corrosion. The corrosion is a redox reaction that is essentially ubiquitous. It's a type of oxidation. The iron ore and most ores found in the ground, if they are reactive enough, will be found in a highly oxidized form, the hematite ores. And this is because this is a spontaneous process. So iron will start by converting to iron 2+. And then the iron 2+ will convert to magnetite, which is a mixed iron 3, iron 4 oxide. And then it will fully convert to hematite, which is iron 3+. We lose a lot of different properties as it goes. For example, solubility changes, strength changes. Hematite is very brittle. Iron and iron oxide is very strong. It was like iron, standard iron, and magnetite is very strong. Magnetism drops down to 0 at hematite, or very close to 0, but magnetite is magnetic. Iron is very, very magnetic. But this process does not occur by itself. To corrode, we need oxygen or some other oxidizing agent. Protons can be used, so acid or oxygen are very good oxidizing agents, and we need electrolyte. So dry iron stored in a dry environment is not really going to oxidize. But if you allow moisture to get on it, and there's plenty of oxygen, it will start to corrode. Or if you acid, which there is a trace amounts of acid in water, but especially in acid rain or just natural rainwater is mildly acidic, these can help oxidize this on several processes. But in order to make iron last longer, we will create various alloys. We will create alloys, stainless steel, we'll put in chromium that helps change its redox potential, but we can also coat it and make a heterogeneous alloy known as galvanized steel. So we coat it with zinc, which is a more reactive metal. So part of my PhD involved studying galvanization process and trying to do this on the nano scale. But the basic process in industry is you essentially very carefully clean off the iron surface so that we can get a clean binding between iron and zinc. That essentially we burn off any rust, we rinse it off, we kind of pickling and fluxing to make sure as we're hot dipping this in there that it's not oxidizing. And then as you dip it in the molten zinc, and the zinc forms a thin layer of zinc all around the steel. Basically a candy-coated shell. Now, over time, this zinc can convert to zinc oxide and even zinc carbonate as carbon dioxide binds to the surface. But this reaction serves several purposes and protects it for years to come. The first is that this shell is a lot more dense, and it does not easily allow oxygen to trickle through and migrate to the iron surface. That it kind of blocks the oxygen out. Iron will allow oxygen in It may not be a fast process, but the oxygen can kind of sneak through the crystal structure and slowly oxidize it from the outside in. But zinc oxide, once it forms, kind of blocks oxygen from trickling in. And zinc carbonate as well. That we form this shell that keeps oxygen out. And this is especially true for as it rusts. Rust, the hematite, is very porous and highly soluble. So like it actually acts as a catalyst for more rusting. So as we rust the surface, oxidize the surface, it binds moisture better and makes it easier for the interior to rust more. But zinc oxide will essentially keep that off. Now, if for whatever reason the iron does get oxidized, zinc acts as a sacrificial electrode. If there is any unoxidized zinc, that zinc, being higher up on the redox potential table, will reduce the iron back to its native iron solid state and get oxidized in its place. So by this way, as long as the zinc is in contact with the iron, it will keep oxidizing itself and protecting the iron for as long as it has some energy left. So this process is not perfect. It will greatly extend the life of most steel products. So sometimes we dip them in. Sometimes we just put in like a big bar of zinc. Like if you have underground like tanks of steel that you can't easily dip in big baths to coat it in zinc, they'll put in zinc bars that essentially it will act as a sacrificial electrode. As the iron tank starts to try to corrode, the zinc will reduce it back down. And so as long as there's zinc remaining, it will keep working to do this. But that is the end of this chapter. The last chapter we will discuss is nuclear chemistry, and so be looking forward to that.